Okay, welcome to lecture here. We're continuing on in chapter 18, I think, electrochemistry. So we'll lecture here, and remember we do have a quiz coming up later on thermodynamics. That's the start of lab. So we've been talking about electrochemistry, and last time we sort of transitioned a little bit in the sense of tying together galvanic cells and sort of cell potential to some of those thermodynamic sort of properties like delta G, also like the equilibrium constant as well. We saw a couple of formulas that sort of tied those guys together. We had one where we had the delta G is equal to minus NFE. That obviously tying together our delta G value and our E of our cell, as we talked about last time. That's really why when we talk about sort of a positive cell voltage, that results in, as we saw last time, a negative delta G, which means reaction is spontaneous. And those things sort of tied into our equilibrium constant would imply that the reaction is spontaneous. It would be heading towards the product side, and we would obviously perhaps expect a larger value for K because of that, as we would have more products than, say, reactants. Opposite would be true, obviously, if we ended up with some negative cell voltage. Negative cell voltage would result in a positive delta G, meaning the reaction is non-spontaneous, meaning it's pretty much hanging out over there on the reactant side, which means we would expect, obviously, a lower value of K. We also saw, again, an equation, which is our E is equal to RT NF natural log of K, one that relates directly sort of our equilibrium constant to the cell voltage. And obviously the same sort of results would happen in terms of positive voltage and larger K value, negative voltage, smaller K value. And we finished up sort of talking about last time what happens as we sort of play with the concentrations, if you will. Something sort of under non-standard conditions, if you want to kind of think about it that way. Remember, when we talk about sort of standard conditions, we're talking usually in terms of like table type conditions where you look up values in tables, and that usually results in a 25-degree Celsius in terms of the temperature. 1 molar in terms of concentrations if you're dealing with any type of solutions. Also, if you happen to be dealing with gases, 1 atmosphere in terms of the pressure is considered standard. Anything sort of outside of that will obviously affect perhaps the cell voltage, like the last example I think we finished up on last time. We would use the Nernst equation, and the Nernst equation is basically our excuse me, our E is equal to E naught minus RT and F natural log of Q, Q being our reaction quotient, and obviously E naught being our cathode minus anode, and the other E being sort of what the cell voltage would be under these sort of non-standard conditions. Any questions on any of that stuff we sort of talked about last time? Okay, so I think we left off right here at this example. So why don't you take a few minutes here and let's go with this one here. We're actually looking for what is the value of E naught and also the equilibrium constant here for this reaction. And again, those are the SRP values and reactions that you would get from the table on the bottom. So take a few minutes and we'll talk about it and see where everybody ends up. Okay, let's take a look at this one, see how we're doing. So we had a variety of different sort of formulas to sort of get us to some places here when we're doing calculations. So as we talked about before, you kind of want to choose maybe the one that applies. So I definitely see some equilibrium constant involved here, got an E of the naught. So we do want to use that one that pretty much has both of those things, and that was the E naught equals RT and F natural log of K. Remember that this sort of comes from that Nernst equation. So at equilibrium, E would equal 0, Q would equal K. And when you do that, that's sort of how you get back up to there. So we would want to use this equation here. We want to calculate E of the cell. So that's going to be our, and again, whichever way you're sort of doing it, I again will do the subtraction. So I'm going to do my cathode minus my anode. So in this particular case, we do want to kind of figure those things out. And again, if you are given an equation like we were here, you do need to actually look at what's going on in that equation to make sure that you know which one's being oxidized, which one's being reduced. If you look at our chromium here, it's going from +2 to +3. It's becoming more positive. So our chromium's actually being oxidized, which means in this case, this guy right here is going to be our anode. And our sulfur here is actually being reduced like a 2.5 to like a 2 on that side, believe it or not. And again, it is getting reduced in that case, also losing oxygen as it goes to the right as well. So this guy would be our cathode. Remember, you don't want to just go by these numbers if you are given the formula, because they may not always be correct in terms of the one that's more positive. So that means that we can calculate our E of our cell here, and that would then be our cathode, which was 0.17 volts, minus our anode, which was minus 0.5 volts. Again, I'm not going to change the sign because I'm subtracting, and that will give us a cell voltage of 0.67 volts. Any questions on that so far?
Professor?
Yeah.
How do you know if the reaction is at equilibrium so you know that E equals 0?
Yeah, so the big kind of hint is actually in the question, it asks for the equilibrium constant. So it's pretty safe to assume that this guy has reached equilibrium. So, it'll mention something like that, maybe in words, or if you're asked to calculate the equilibrium constant like we did here, that would be a good sign that you're probably at equilibrium. Or if they give you an equilibrium constant value, you also would know that you're at equilibrium. So they will give you some type of hint, if you will, in terms of that you're probably at equilibrium. The way you would also know that you might not need to use the Nernst equation is also just by what's given to you or not given to you here in this reaction, right? We're not given really any concentrations or pressures or anything like that, which means you can't really calculate Q or anything like that. So, that's also a good thing to think about.
Okay, thank you.
Welcome. Other questions? Okay, so we got our E of the cell here. And again, we're going with our equation here that does obviously have the K. So we now have E, R is a constant, our temperature there, it doesn't say it, but we'll assume it's 25 degrees, which would be 298.8. Also a pretty safe assumption if they happen not to give you a temperature, probably safe to assume it's 298 or 25 degrees. F is a constant. So really, we do need to figure out N. So remember that, technically speaking, we are flipping the bottom equation there. And that will give us something like this. And our E naught technically would swap signs, and that's why we would add if we were kind of doing that approach. But if we were going to add these together, we do see we need to times this whole thing by 2 to get the proper number of electrons. And obviously, that will give us our overall reaction that's balanced in this case. So 2 is going to be really our N here. Remember, N is the number of moles of electrons, not the total for if you add both half reactions. Again, it's really the balanced number of electrons in the anode going to the cathode. So it's the same number of electrons. If you think about it, kind of going across the wire to the other side. So that at that point there should give us everything we need. So we will go with 0.67 is going to equal our R, which is our 8.314. Our temperature at 298. divided by our N, which was 2, and our Faraday's constant, which is 96,500 joules per volt per mole. And probably a bad choice to write it right there, but I'll go natural log of K to the right of that is where we should have. So kind of cleaning up everything on the right-hand side. So that's going to get us 8.314 times 298 divided by 2 and divided by 96.5. It's going to get us 0.67 is equal to 0.012837 natural log of K. Now I got room for it. We're going to divide that to the other side. Going to get us something in the ballpark of 52.1922 equals the natural log of K. We're going to E both sides there. That's going to get rid of the natural log, and that will give us a K value of like 4.6 to the 22, looks like.
Professor,
Yeah.
what happened to, because like the equation up above says E equals E cell minus that whole equation. So, oh, okay, just kidding. Sorry, never mind. I saw we're using the equation up above.
Right, we are, and that's because we're at equilibrium conditions at this point. So kind of the Nernst equation at equilibrium kind of reduces down to this equation we saw earlier. And so that's sort of where that equation sort of comes out. And that's because, again, at equilibrium, that E would equal 0. And if we're at equilibrium, we're not talking about the reaction quotient, but we're talking about the equilibrium constant. Yeah, so that Nernst equation kind of reduces down to that. I think we saw this equation actually before the Nernst equation. That's sort of where it comes from. Other questions on that? So a couple things does make sense, right? We obviously, see some results that we might expect. We obviously have a positive cell voltage. That should give us a negative delta G, which means the reaction should be spontaneous. Should be heading towards the product side. Heading towards the product side means we should have a larger value for K, and we do. So all those things, again, agree with each other. Question on this calculation, E of the cell, delta G, K, all those things. Okay. So the next thing we're going to kind of talk about is batteries. We're going to talk about some different types of batteries. Talk a little bit about how, they're kind of similar to a traditional galvanic cell in a lab and how they differ a little bit. I'm not going to probably ask you any specific half reactions or any type of battery or anything like that. So it's just sort of basic knowledge, I'll put it that way, kind of basic knowledge in terms of, kind of similarities between batteries and sort of galvanic cells, or sort of how they're similar and different. So you don't have to worry about anything sort of specific in a lot of these slides we're going to kind of go through. But first off, we'll talk about a battery. A battery really is, a series really of galvanic cells, or a series of galvanic cells sort of put together, where we use it as a direct electrical current at constant voltage. A couple of differences, obviously, between a battery and a traditional sort of galvanic cell, like we've been talking about in the laboratory, is clearly the setup there, right? So we typically in a laboratory have a galvanic cell sort of set up like this. Clearly a lot of liquids and stuff like that, which would not go great with electronic devices. So in a battery, it's kind of self-contained. We also don't have a traditional sort of salt bridge like we do here in sort of the laboratory version of a galvanic cell. There are other sort of properties within the battery that act or sort of function as like a salt bridge to kind of keep everything moving and stuff like that. But obviously, one major difference, obviously, between a battery and a galvanic cell is just that process of it being really self-contained and not obviously beakers of solutions and stuff like that, which obviously wouldn't work so well. So let's first talk about the first type of cell, sometimes referred to as a dry cell. And we can go with Duracell there, perhaps. And that's basically a cell without any type of fluid compartment. At the anode, we have a zinc can or container. And here's sort of our anode down here, right? Negative side, kind of visual electrons traveling kind of back around, right, towards the positive side. When you put a battery into a compartment, right, there's a lot of wires usually, right, that they kind of hook up to. Again, very similar to like the wire that hooks one galvanic cell or one compartment of the galvanic cell to another, to where the electrons basically transfer across. So sort of the same idea. It's in a contact with a strong electrolyte or an electrolyte sort of solution in here. This electrolyte, what's an electrolyte? Well, an electrolyte, right, is something that breaks apart into sort of ions, helps keep everything flowing. Again, sort of like our salt bridge in a traditional galvanic cell. The cathode is our carbon rod, which is the guy coming through the center here, and immersed also in that electrolyte solution. So again, sort of that paste in the electrolyte solutions really acting very much like a sort of salt bridge to keep everything sort of flowing. These type of batteries, regardless of sort of size, C, A, double A, I guess, triple A, they all have really the same voltage. They give off about 1.5 volts. And these were actually our two sort of half reactions that are happening here in a battery such as this. We see our zinc going from 0 to +2, again, being oxidized and being our anode. And down here, right, we have our, excuse me, our Mn, for example, going from like +4 on this side. What's happening to our Mn on this side to like +3, right? Getting reduced as well. So we do have this sort of reduction happening here. Also, we have some ammonium in there as well happening. And again, this is our overall reaction that is happening. The differences in sizes, right? You know, a C battery, a D battery, whatever it may be, right? Just means it, you know, could kind of progress this reaction over and over for a little bit longer period of time than, say, a smaller battery would. Another type of battery is a mercury battery, and a mercury battery it's used a lot in sort of medicine and electronic industry. It's a little bit more expensive than a dry cell, and it also has a similar sort of setup. It's got our anode, which is again zinc that's in with a little bit of mercury in there, and it's in contact with a really strongly alkaline electrolyte. Strongly alkaline means basic, right? That's what alkaline means. So that's basic. So really like a strong base, like KOH, like potassium hydroxide, as we see in the picture. Strong base would also be a strong electrolyte. Again, acting really kind of like our salt bridge, keeping everything flowing in terms of the electrons and so forth. The nice thing about this is there's kind of no change in the electrolyte composition during operation, which means it doesn't really degrade all that much, which is why, you know, it can last a fairly long time, this battery, before it really starts to, you know, kind of go down overall. It's high capacity and longer life. Again, sort of that really no change occurring in the electrolyte solution really helps in that aspect. It has a little smaller voltage of 1.35 volts. And again, here we do see our sort of zinc going from 0 to +2, and our mercury as well going in this direction. One major sort of thing that also allows it to be sort of longer lasting and stuff is when we look at batteries, and if we see in the overall reaction a lot of solids sort of being generated, that usually allows the battery to, for example, is very big in sort of rechargeable type batteries, having that sort of guys, it allows the reaction to be sort of reversed by recharging it and keeping this battery kind of going for a good bit of time. Lead storage batteries are really like our car batteries that we have in our cars, our gas cars there. And they're basically 6 identical sort of cells joined together. Each one gives off about 2 volts for your 12-volt battery that you need basically to start your car. That's enough when you turn it right, except when you're late and your car doesn't want to start because your battery's dead. But if you turn it, it will hopefully be enough to get everything kind of going and starting. It's rechargeable. So, as we sort of drive and as this reaction goes, it's sort of regenerating the battery as well, which is why sometimes if you ever jumped your car, they tell you, hey, let it run for a bit before you shut it off. Otherwise, it's going to be dead again. So it gives it a little chance to sort of rebuild some of that and recharging as it goes through it. And here's sort of a cross section of a car battery. And the big question is always, right, like we talked about maybe the other day in lab, you got your jumper cables out, you got your red one, you got your black one. Which one do you put on to which? So, we have our anode and our cathode side here. Usually we have the sort of battery acid in there. So obviously something like sulfuric acid, which is a strong electrolyte, because it's a strong acid, again, ultimately sort of functioning like our salt bridge, keeping everything flowing. Our anode reaction, we got our lead going from kind of 0 to +2 over here. And when we look down here as well, we see a lot of solids, which again is very good for keeping this reaction or this battery kind of going for a good period of time. Nowadays, a lot of times batteries actually are not in the engine compartment, and a lot of cars, they're actually sometimes in the trunk or under the back seat, but they have the spot where you could jump it kind of in the engine and stuff like that. Sometimes people are surprised, they open their engine and go, where's my battery? But nowadays sometimes they put it like in the trunk or under the back seat and stuff like that, which is an interesting thing. Another type of battery is a lithium, solid state lithium battery. The anode is basically a carbon type of substance like graphite. It has little holes that allows the lithium really to go from 0 to +1, again being oxidized and sort of traveling across here and so forth. It's a solid state, which means it can be recharged hundreds and hundreds of times, as I mentioned earlier. Sort of that overall reaction where we kind of get sort of solid products and things aren't sort of degraded down in the process of the battery running, allows for things to be rechargeable and stuff like that. Lithium is also a light metal, right? So lithium ion batteries and stuff like that, right? Power tools and stuff like that. So they use, obviously, this type of battery a lot of times in those applications, again, for the fact that you can recharge it a lot. It's also very light, so you're not lugging around a very heavy battery as you're trying to, cut your lawn or use your power drill or whatever you may be using nowadays. Now, a fuel cell is also not technically sort of really a battery, but it does function sort of very similar to a battery. This is a hydrogen fuel cell, and this obviously was years ago sort of the idea of what they maybe wanted to turn cars into, kind of switch over from gas to sort of a hydrogen sort of car, and using that. And the reason for that is, as we could look at sort of our overall reaction here, we're basically making water, right? So obviously a way we can maybe cut down on some pollution and stuff like that. Obviously it involves hydrogen being pumped in, which is typically what you would fill up your gas tank with. Oxygen obviously would probably come from just the street as you're driving through, right? The air vents and all that. Those guys mixing again, producing sort of the battery operation of it and the power. And the idea behind it was, hey, we're just going to spit out basically water from the tailpipe. Everything's good in that. Obviously, that requires a lot of changes to sort of, gas stations and stuff like that and where you would fill up. So we've obviously now moved more towards the hybrid model, and obviously now moving into the straight battery model for a lot of cars and stuff like that. So a lot of electrical vehicles rather than, this type of system. So that's a little bit about some batteries. Again, I'm not going to ask you any specific reactions about any of the batteries that we discussed. You do just kind of need to know the similarities between, a traditional galvanic cell and maybe a battery, and obviously some of the maybe differences between the two. Any questions on that there? Okay, then we're going to talk about corrosion and sort of a little bit about what corrosion is, sort of how it happens, and a little bit about, maybe some ways to prevent corrosion. So let's talk a little bit about, I guess, sort of corrosion and sort of what it is or what happens when it occurs. Corrosion is really sort of returning metals to their natural state. It's really the oxidation of metals is basically what a lot of corrosion is basically when metals go through oxidation. A half of or a fifth of steel is to replace, rusted out metals. All metals that have an SRP value less positive than oxygen are susceptible to going through corrosion. So what does that mean? So if we have an SRP value that's less positive than oxygen gas, like the stuff's flying around all over the place here, right? What does that mean in terms of like our galvanic cell, for example, right? Well, that would mean that oxygen would have a more positive SRP value, which means if we were trying to assign where oxygen would end up in terms of it being the anode or cathode, oxygen would end up being our cathode, right? Where reduction would take place. What does that mean with a metal that's sort of hooked up with oxygen? Because it has an SRP value less positive than oxygen, that means our metal is going to be our anode, which means our metal is pretty much going to go through oxidation. So metals that again have that sort of SRP value that's less positive than oxygen in a natural sort of process is going to set up really a galvanic cell that's going to be spontaneous. It's going to require basically that metal being oxidized, which in certain cases is not a very good thing for metals. It can pretty much destroy some metals. And it will go really through corrosion. Any questions on that? Now, is all oxidation of metals a terrible thing? And the answer is no, it's not really a terrible thing. Actually, in some cases, when a metal goes through oxidation, it actually can create a layer kind of on top of the metal that actually protects the metal that's underneath it. So for example, aluminum, when it goes through sort of oxidation, it creates this aluminum oxide sort of layer. And although the top layer gets sort of oxidized and goes through this process, all the metal that's underneath that layer is now protected from further oxidation because, that little layer of aluminum oxide basically formed. So again, not necessarily corrosion of all metals are a terrible thing. It can be a really good thing in some cases. It can be a protective thing. In other cases, it can be a really bad thing. And the most obvious case that we are probably familiar with is rust. Basically, when iron goes through oxidation, it does create this layer, but that layer unfortunately falls off. So while iron will go through some oxidation and corrosion, just like the aluminum example over there, the problem though is this guy will fall off. And when it falls off, it obviously exposes fresh metal underneath to also start going through corrosion, which then will eventually fall off. And before you know it, you have the big hole right between the metal and stuff like that, because basically you rusted kind of right through it. So again, in certain cases, it can be okay, the oxidation of these metals or the corrosion of these metals. But again, in other cases, it cannot be so great either. Copper forms a nice, pretty greenish carbonate patina. People pay a lot of money sometimes for that patina sort of look. So, again, not always such a bad thing. When silver tarnishes is silver sulfide. Gold at 1.5 volt is larger than oxygen, so there's no appreciable corrosion of gold. So what happens with gold metal when it hooks up with oxygen? Because gold's SRP value in this case is actually more positive, than oxygen. When these two metals get together, the gold is actually the cathode. And basically where a reduction takes place, the oxygen gas then becomes the anode, and where oxidation occurs. So because when these two guys get together and gold's really SRP value, actually you won't see obviously corrosion occurring with gold metal because of that, because basically in that situation, again, thinking about it in terms of a galvanic cell, our gold is actually going to be our cathode, while all the sort of bad oxidation is going to actually occur at the oxygen side. Looking a little closer sort of at rust, there's really a few things that you need for sort of rust to occur. You basically need some iron, you need a little bit of oxygen and some moisture, and those are really, all the good parts that are needed for rust basically to form. Rust occurs in sort of a couple of processes. First, the iron gets oxidized to iron 2. Electrons flow through the steel to the cathode. Again, here the oxygen going to be acting as the cathode, again gaining those electrons, and then the iron 2 actually then gets further oxidized to iron 3 oxide, and we do make that rust. Again, there's a lot of non-uniform sort of spots on steel that makes for really good pockets for this process to occur, for moisture to sort of sit in there and allow that sort of oxidation and corrosion to occur. Here's a much prettier picture than what I was sort of describing. But again, we get these sort of pockets where, moisture could really sit. It's going to allow that oxidation of iron again to go from +2, then to +3, and that whole process. And again, the bad news here is, unfortunately, that's not very protective, because it can kind of really just come off fairly, easily and stuff like that. Obviously, at some point, you're just going to kind of eat away, and you're probably going to need to replace that piece of iron or steel. Going to cost some money, and that's why things are, not so good when we get iron going through oxidation. How can we prevent some of this corrosion? Well, there's different ways that you could kind of prevent corrosion of metals along the way. And one is to basically provide your own sort of layer of protection for the metal. You could paint it, right? You could also metal plate it, right? They sell a whole line of paints called Rust-Oleum paints, because, you can paint it and kind of provide protection, hopefully, for your metals. You could also plate it with some other sort of metals that will create a sort of protective layer for the metals that are underneath it, like galvanizing, for example. When we galvanize, it's sort of a mix of oxide and carbonate coatings. Zinc is a more active metal than iron. So again, when we kind of put that layer of zinc in there, and we look at these two things, now between these two metals, which are there, the iron, which wouldn't be there by itself, and then we add some zinc. When we look at these two guys, the SRP values here, we now see that actually iron becomes more positive and zinc is more negative, which means that the zinc in this case, with that being there in comparison to the iron, will now take up the role of the anode, and our iron will be more the cathode in this case. So we're kind of, by galvanizing, adding the zinc, sort of moving the oxidation over to zinc. Zinc again will provide perhaps a layer of protection as it's going through that oxidation, and sort of coats it and protects obviously the iron that's underneath it. We sort of are sacrificing, if you will, sometimes referred to as a sacrificial sort of coating. So we get all the bad oxidation happening on it, really protecting the metal that's sort of the structure of whatever you may be using that's underneath it. Alloying is another way that we can kind of prevent corrosion, again, by adding some other metals in there. We're able to change some of the SRP values for certain things to more noble metals. By the way, noble metals are like our gold or silver or platinum. These are guys that are really basically chemically inert, not very reactive, just like we talked about with gold a second ago with that SRP value, not going to go through pretty much much of any type of corrosion. And again, by adding some of these extra sort of metals in there as sort of a protective mixing of layers is going to kind of turn our normal metal that would go through corrosion into a metal that's very similar to those noble metals and be protected. That's also sometimes what they used to use there, and when they would bury tanks underneath the ground and stuff like that. Obviously, when you do that, there's a lot of moisture underneath there, and especially if you happen to be dumping a iron tank underneath the ground, obviously that is just a recipe for a lot of corrosion that's going to occur. So you could attach something like magnesium, for example, to a wire to that tank. And what that's going to do is magnesium is a better reducing agent than iron. So what does that mean if magnesium is a better reducing agent? Reducing agents are the things that get oxidized. So what that means is by having that magnesium present, all the oxidation is pretty much going to occur on the magnesium site and not where the iron tank is sort of buried under the ground. That obviously is important because the iron tank is probably the thing that's holding on to what you don't want to sort of spill out of it and stuff like that. So it allows sort of again, another sort of sacrificial sort of metal to take sort of the brunt of all the oxidation that would occur. And again, sort of adding a protection to the metal that you're trying to keep in one piece. Here's sort of a picture of that again. Without the sort of magnesium here, you know, we would have all the oxidation occurring probably right here on our iron tank, which is not so good. With the magnesium being present, we now, again, like I mentioned, moves the oxidation over here, turning this guy really into our anode and sort of our cathode kind of happening over here. Again, all the sort of bad things happening to the magnesium, hopefully protecting the storage tank there and keep it in one piece. Obviously, as I mentioned, you do have to kind of go through and obviously perhaps replace that. Any questions on corrosion? So what you need to know is basically what corrosion is, why it takes place, a couple of ways to prevent corrosion. And I think that's sufficient. Any questions on that? Okay, the last thing we're going to talk about in this chapter is electrolysis. Electrolysis is the process where we make really a non-spontaneous process sort of occur by, you know, adding some extra electrical energy. So for example, under normal conditions, right, you know, if we took something like sodium chloride, you know, under normal conditions, we really don't get, you know, sodium metal back and chlorine gas back, right? You know, that is like under normal sort of situations, not going to really happen spontaneously. Otherwise, when we, you know, eat our fries, that would be a very bad thing, right? Especially if you just heated it up in the fryer there and all this kind of stuff would happen out of there. That wouldn't be so good. But we can't do it by really running an electrical current, say across a sodium chloride or even water as well. Is a process where we do that, and that's what's known as electrolysis. It makes a chemical reaction occur, and we actually can sort of break these guys back down into their basically elements, if you will. We throw some sodium chloride in there, we will get some chlorine gas that will come out. We'll also get some liquid sodium coming back out, as we can see over here in this sort of process. What is happening in this case? Well, we are essentially, if you think about sodium chloride, which is an ionic compound, it's really sodium ion and a chloride ion here. And if we're going to do this sort of electrolysis process, we want to kind of bring these guys back to like their original sort of state. And that means that technically speaking, we want to take that sodium ion back to sodium, really solid, but liquid. In this case, it will come out as molten liquid. And we want to take the chloride back to really chlorine gas. So what is happening in terms of like our what is being oxidized and what is being reduced in this case might be a little bit different than you think. In this case, we're going from +1 to really 0 here for our sodium ion. We're going from -1 here to 0 for our chlorine ion. What does that mean? Well, that means that our sodium is becoming more negative, which means it is actually the thing going through a reduction here. Our chlorine is becoming more positive, which means it is actually going through the oxidation here and actually is our anode in this sort of electrolysis reaction. And again, you could kind of think about it as the opposite of, when we make sodium chloride, right? When we make sodium chloride kind of go in this direction, and I won't balance it, but we'll just kind of go this way. We're really going from 0 to +1, right? It is losing electrons when we make it. Going from 0 to -1, it's gaining electrons when we make it. So again, the electrolysis, you could almost think of it as sort of the reverse reaction, if you will. And that's again why the oxidation is actually happening here in our chloride and our reduction is happening in our sodium. Any questions on that there? Now, this is the electrolysis of water, and you might have done this in Chem 3. They do it, right? You could do this very simply with like a 9-volt battery basically hooked up to some electrodes and some acidic water there. And you basically could get water to break back down into hydrogen gas and oxygen gas. Obviously not balanced, but put a 2 there, right? And like a 2 there perhaps, and we're good. And it will start to bubble, and you'll see that. And usually we do this with some dilute sulfuric acid or some type of acid water. In fact, if you remember this experiment, and you were in person, I suppose, at college here in Chem 3, you did this, and there was a big bottle of like acid water was sitting there. And really the acid water is going to provide a lot of the H pluses that are going to be needed for that reduction reaction to sort of occur pretty easily here or better here. And that's what we're talking about here is sort of this production, having a little greater concentration of the H plus is going to happen in this case. So what's happening here is we run electrical current over it. We're going to break the water off into basically oxygen gas and hydrogen gas being made. This is the bubbles that we see in this picture, also the bubbles that we see here in the test tube over here in a real life picture. And you might even be familiar with the outcome here. They use really small like test tubes those days are in Chem 3, but this empty area here, which is really not empty, that is where our hydrogen gas is. And then again, this spot here, which is really not empty, is really where all of our oxygen gas ends up, right? The gas goes in, the water goes out, basically, kind of a displacement sort of situation. And what do we see here? We see here what we've talked about in terms of formula, probably you've talked about in terms of formula before. There's like 2 hydrogens for every 1 oxygen. You get like twice the amount of hydrogen gas as you do oxygen gas generated in that particular case. And again, this is known as the electrolysis of water. Now, when you're doing electrolysis problems and they're involving really the electrolysis of water, sometimes they don't straight up come out and go, hey, we're dealing with the electrolysis of water right now. This is an electrolysis of water type problem. They oftentimes will mention actually something about like sulfuric acid, some type of acid solution. So if you get some type of problem where they mention something about sulfuric acid be involved or some type of acid and nothing really else mentioned about what's happening in the electrolysis cell, they're most likely referring to the electrolysis of water. And again, that's sort of the key word that you will see sometimes in problems, especially they might not just straight out come out and say, hey, we're doing the electrolysis of water. And what that means is if you need the half reactions, these would be the correct half reactions to use in that sort of calculation. Any questions on that there? So let us actually talk about how to do these electrolysis sort of calculations. They're fairly straightforward in terms of the calculations that you'll need to do with these guys. And they're either, it happens sort of in one direction or the other, and we'll talk about that in just a second. But the couple of processes there are on the left in terms of the calculations, you want to take the amperage and the seconds, and that's really the current in amperage and the time that the cell runs for. You want to figure out the charge in coulombs, and that's going to require you to use our Faraday's constant that we've used before. You then want to take the number of moles of electrons, and you want to use those and the half reactions basically to figure out for every number of electrons you have in a half reaction, a balanced half reaction, how many moles of whatever you're looking at, how many moles of sodium you may be looking at, how many moles of chlorine, or how many moles of oxygen or hydrogen that you may be looking at. You then can either solve for grams or liters of product. Now, for example, in the case of water, we're dealing with a lot of times gases. So sometimes in these electrolysis problems, you do need to use the ideal gas law, PV equals nRT. I was going to divide it by something, but I don't know why I did it there. And that's because a lot of times you will solve for V is equal to nRT over P. There's my dividing. And in this case, you would probably be given the temperature, you'd be given the pressure. Ours is the gas constant, which is our 0.08206 version there. Kelvin. So you'll be figuring out the moles of like oxygen gas or hydrogen gas, and then you would solve for volume. So again, that's sort of a common sort of calculation that you sometimes need to do. A coulomb is equal to an amp times a second is also another important sort of relationship there. And rearranging that, because you often are given the amperage of these cells, an amp would be a coulomb times second. So a lot of times we need to get rid of the seconds part. So they'll tell you, hey, you ran the cell for, 42 hours. So a lot of times you need to take like the time, maybe to minutes, maybe to seconds, to make sure that the time ends up in seconds. So whatever time they give you for how long this particular cell ran for, you need to probably convert it to seconds. And then essentially you kind of do this sort of calculation. You take the amperage, which is really the coulombs per second, you times it by the seconds that the cell ran for. That gives you the coulombs of this cell. You then use our Faraday's constant here as a conversion factor to go from coulombs to moles of electrons. And where do you find your moles of electrons? Well, you find your moles of electrons from the half reaction. So you should have a half reaction. That's your oxidation half reaction. You should have a half reaction. That's your reduction half reaction in this electrolysis cell. And you're going to use those to go from moles of electrons to moles of, your substance that you're interested in. Again, maybe like oxygen gas, nitrogen gas, and I'll get you moles of your element, really. I guess I could put it that way. And at that point, you could either molar mass to get to grams, or you can, like I said, use the PV equals nRT perhaps to get to liters or volume. So that's the common sort of mathematical route for these type of problems. The opposite sort of calculation would be they tell you how much is produced, and you basically go backwards. So those are sort of the two common ways that these calculations for electrolysis cells are done. Either they tell you how long the cell ran for and what was the amperage, or they tell you, hey, you produced this much, with this much amperage, how long did it run for? Or you produced this much and it ran for this long, what was the amperage? So it's kind of a similar calculation, just whichever way you're sort of heading. Any questions on that there? All right, so let us take a look maybe at one here and see what we could do. Actually, I'm going to skip this and we'll come back to this one. And we'll start with this one here just to kind of show you how this sort of calculation goes here. So in this case, we want to know how much calcium is produced in a basically electrolysis cell of calcium chloride as a current is passed, that is 0.452 amperage, and we ran this cell basically for 1.5 hours. All right. So in this case, what we want to figure out is we're obviously doing our calcium chloride. Again, when we're talking about calcium chloride here, this basically is calcium ion and 2 chloride ions. Remember that when we do the electrolysis cell, we're essentially going to send this thing backwards, right? Kind of back to where they came from. So you could find these half reactions, you know, probably up there on the SRP table if you're not sure with it. But in this case, our anode would be our chloride. And let me get that arrow out of the way there. And again, remembering, since we're sort of going backwards in what's happening here, we want to take the chloride back to chlorine gas in this case, which is sort of its natural state. Again, going from -1 to 0, becoming more positive and going through oxidation. We also want to take our calcium back from a +2 charge, basically to no charge at all, our solid, and that is going from +2 to 0, becoming more negative and going through a reduction. So it's very common, because people don't realize we're kind of going backwards, if you will, from where these guys came from. They oftentimes will reverse sort of our anode and our cathode. Any questions on that so far? All right, so taking the piece of information given to us, and we got 2 pieces of information really given to us. We have that we ran this guy at 0.452 amps. That is the same as 0.452 coulombs per second. Again, an amp is a coulomb over a second. That's where our time comes into play. We ran the cell for 1.5 hours. So we do need to convert that time into seconds so that all the units cancel. Obviously, our time right now is in seconds here. So we're going to convert our 1.5 hours. In 1 hour, there's like 3,600 seconds, I believe. That gives you 5,400 seconds as basically how long we ran this particular cell for. So we're just really converting units. Again, we're converting units here so that everything cancels out correctly. So basically what we're going to do is we're going to times this by how long we ran the cell for, again in the same units. The seconds will cancel each other out, and we will end up with 2440.8 coulombs in this case. Any questions on that so far? So basically we're going to take the current basically and times it by the time here. And that's going to give us basically the electrical charge. This is where Faraday's constant comes into play. We will take Faraday's constant and convert that charge into moles of electron. And again, it's the same Faraday's constant we used previously, 96,500 moles, moles of electrons on top and coulomb on the bottom there. Coulombs are going to cancel, and that will get us we'll call it 0.0253. All right, so now that I have moles of electrons, this is actually where our half reactions are going to come into place. So now that I know the moles of electrons, I'm interested in this case about how much calcium we're going to produce. So going to the half reaction that involves calcium metal, and the electrons there, we see kind of like stoichiometry that for every 2 moles of electrons, we get 1 mole of calcium in this case. And that's what we're going to use to go from moles of electrons to basically moles of calcium. So 2 moles of electrons, 1 mole of calcium, again, coming from the balanced half reaction to do that. And that gets us something like 0.0126 moles of calcium at this point. Any questions on that so far? We're close to figuring out how many grams of calcium we would actually produce. So since we have moles of calcium, to get to grams from moles, we hopefully know this. We go to the periodic table and we find 4008 grams per mole as the molar mass of calcium. So to finish up this calculation, we would take our 0.0126 moles of calcium, using the molar mass from the periodic table, 4008 grams per mole of calcium will get us 0.51, we'll call it 0.51 grams of calcium would be made in this cell. Any questions on that calculation? So what this means is if we ran the cell at 0.452 amps for 1.5 hours, we should get out, spit it out there, basically 0.51 grams of molten calcium coming out of that electrolysis cell. Any questions on any of that part there? Now, could we also figure out how many grams of calcium we would, or chlorine we would produce? We could. So it would be the same idea. We actually would pick it up right here with our moles of electrons. So for example, if we were interested in grams of calcium, maybe our chlorine. So we would pick it up with our 0.0253 moles of electrons. We would then go into our half reaction and find a relationship between electrons and chlorine gas. And in this case, for every 2 moles of electrons, we get 1 mole of Cl2. And that's what we would use for our conversion here. For every 2 moles of electrons, 1 mole of Cl2. And at that case, you would end up with 0.0127, we'll call it, moles of Cl2. At this point, if you wanted to, you could molar mass and get grams of Cl2. If you wanted to and you had the pressure and temperature given to you, you could PV equals nRT and get the volume of chlorine gas. So you have a couple of options in terms of how you could get there. Question on this electrolysis sort of problem here. All right, now that I did that one, why don't you give this one a go here. Let's do the electrolysis of water here and see what you come up with. All right, so we're looking for, we have a current of 1.26 amps. This passed through a cell of sulfuric acid for 7.44 hours. Write the half cell reactions and calculate the volume of the gases generated. So this is what I was talking about earlier. No mention of water here, but mention of sulfuric acid. And again, that tells you that we're dealing with the electrolysis of water. So we would have our half reactions here. And actually, I think it's on the next page here. So I'll just write them here so you have them. And we're dealing with these half reactions that we saw in that electrolysis of water. Let me just put the other information up here. It's 1.26 amperage for 7.44 hours at STP. We're looking for the volume of each gas. Hopefully, you know the gases we're talking about is oxygen gas and hydrogen gas. Yes. So we're looking for oxygen gas and hydrogen gas. So I want to take a few minutes here, see what you come up with. I'll also give you a reminder in case you don't remember, STP means 273 Kelvin and 1 atmosphere, just in case. All right, take a few minutes and we'll talk about it. Okay, so since we're getting to the end here, let us take a look and see what we got going on this particular one. So in this case, obviously the STP is a pretty big hint that we're probably going to need to use PV equals nRT since we're also dealing with gases. So again, don't forget about that Jim might need to use this guy in sort of these electrolysis problems. The beginning part really does sort of work out the same. We have the amperage. We also have the time. Just like before, in order for everything to cancel out correctly, we do need to get the time into seconds. So you might as well just go and kind of do that up front. So that's going to give us 26,784 seconds. Now that we have our time in seconds, remember that when we have 1.26 amperage, that is basically the same as 1.26 coulombs per second. And again, why we want to get our time into seconds. So we're really going to take the amperage or the current times the time so that everything cancels out. Again, the seconds will cancel out here. And that will get us, looks like we'll call it 7.8, and again this is coulombs. This again is where Faraday's constant will come into play. This is going to get us into our moles of electrons that we need. So 33747.8 coulombs, again dividing by Faraday's constant is going to convert us there into electrons. And looks like we end up with 0.3497. Any questions up to that point? It's really this moles of electrons that allows us really now to go into our half reactions and do one of the guys or both of them, you know, depending on sort of what the question asks. So we're going to, we'll start with, say, the oxygen and the hydrogen. But first, what we want to figure out is, you know, what is the kind of mole to mole relationship for each of those guys. So if we look at oxygen, there is 1 mole for every 4 moles of electrons. So for every 4 moles of electrons, there's 1 mole of oxygen gas. If we look at our H2, and there is a 4 on the outside. So if we actually kind of distribute the 4 to everybody in there, we get a relationship that there is 4 moles of electrons for every 2 moles of H2. That is the same as 2 moles of electrons for every 1 mole of H2. You can use either one. They obviously will come out the same, but we'll just go with this to kind of keep it a little bit less. Any questions on how I got those relationships there? All right, so what is left is let's get the moles of each of those guys. So we'll start with the oxygen here. So moles of O2 would be our moles of electrons. Using our half reaction to figure out our oxygen moles, 1 mole of O2 up on top and 4 moles of electrons on the bottom. Dividing that by 4 gets us 0.0874 moles of oxygen. We also can get our moles of hydrogen the same way. We'll do our 0.3497 moles of electrons. We're going to use our half reaction for hydrogen. And again, you can use either one of those guys. I'm going to do the 2 moles of electrons is 1 mole of H2, or you could do the 4-to-2 relationship, which is obviously the same. Dividing by 2 gets you what we got there? 0.175 looks like. We'll go with 0.175 moles of H2. Any question on how I got those two numbers? All right, well, now that we have that, we know we've got to do a little PV equals nRT action here. We know our temperature is 273 Kelvin. We know our pressure is 1 atmosphere. So we have pressure, we have temperature, R is a constant, and now we have N for everybody. We could use the ideal gas law here to solve for the volume of O2. That would be nRT over P. That's going to give us our moles of oxygen, 0.0874 moles. Our gas constant, 0.08206 liters atmosphere Kelvin mole. Our temperature being 273 Kelvin, all divided by our pressure here, which was 1 atmosphere. Everybody will cancel out except for liters, and we will end up with 1.96 liters of O2 would be collected in this electrolysis cell. Any questions on that one there? Yeah, go ahead.
Do you mind if I use 0.0821?
Yeah, you can use that. It should come out pretty close, I would think. It's fine. Yeah.
Thank you.
I just use that number. I just use that number because it's what they kind of beat in my head. So that's the one I use, but it's okay. 0.0821 is perfectly fine. Yeah. Other questions? Okay. And we could do the exact same thing for hydrogen if we wanted to, but we also could do something else. You might also remember from 1A that when you're at STP conditions, 1 mole of any gas equals 22.414 liters. So you technically could use that instead of the ideal gas law if you wanted to. And you could use that because, again, we're at STP conditions. If we're not at STP conditions, you can't use that, by the way. So because we are at STP conditions, the volume of hydrogen can be found by the same way as there, R. You could just take the moles of hydrogen, which was 0.175 moles, and times it by 22.414 liters is 1 mole. And you will end up with 3.92 liters of hydrogen gas. And again, you can go into the ideal gas law like we did with the oxygen if you wanted to, and you will end up with the exact same answer, basically. Maybe slightly off with some rounding, but pretty darn close to that. So if we ran this cell for the 7.44 hours, we would produce 1.96 liters of oxygen that would bubble up in the test tube, or however you're collecting it. We would produce 3.92 liters of hydrogen that would bubble up in that test tube, or however you're collecting it. Any questions on those calculations there? You will also see what we talked about before. If you compare the amount of hydrogen gas collected to the amount of oxygen gas collected, you collected, as we would expect, 2 times the amount of hydrogen gas per oxygen gas. Again, Y is called H2O, twice the hydrogen per oxygen in this case. Any questions on that? Our electrolysis problems. So you can see a couple of different sort of electrolysis problems. One where we use molar mass at the end to get the grams. Here we obviously are looking at gases, so we use the ideal gas law. Like I said, a variety or variation of this problem would be, they would tell you something like, hey, you collected 3.92 liters of hydrogen gas. You know, you ran it at an amperage of like 2 amps. How long did you run it for? So kind of going backwards again, is sort of a variation on this type of problem. Any questions on electrolysis or how to do those calculations?
Professor,
Yeah.
what would be the half cell reactions? Like what, because I'm guessing that like the volume of gases would be, our answer would be the 3.92 and the 1.96.
Yeah.
But then what would be the half cell reactions?
It would be these up here on top. So this would be your anode.
Okay.
And then this would be your cathode side of the electrolysis cell. And again, here our cathode side, the hydrogen gaining electrons, and really our oxygen here and water on the top one going from -2 to 0 in terms of its oxidation state, which is why it's being oxidized, and it's the anode. But the other part of the question, I just gave it to you because water is kind of a tricky one. But these would be the two half reactions for the electrolysis of water. Other questions on that? Okay, so that actually wraps up this chapter. And as we mentioned earlier, we do have an exam next Wednesday on the thermodynamics chapter and also this chapter as well.